Start the recording. Alrighty. Well, thanks everybody for joining. This is a really cool opportunity to share some of the work that we've been doing with FEMA over the last, it's been over a year now. I think the lead into this has been going on much larger or longer than that. I've been working on some aspect of synthetic weather generation on behalf of the Corps for about 10 years, and then even going back to my master's program, I've always been tinkering with how do I generate fake weather to solve problems. And so what I'm going to do, I'm going to talk mostly about what we've been doing for FEMA, how we're putting it into the software, and some of our goals for collaborating with other partner agencies and other folks who are interested in applying this potentially to some of their projects. Please feel free to interrupt me if you got a question. Use the little raise hand. I usually see that right away, and so if there's anything that you want to ask, if you're curious about, or if you have something that you feel like it'd be easier to type out too, go ahead and use the chat so that I can jump on that, because this doesn't have to be a formal sort of thing. Yes, Will.
Can we record this? Oh, sorry, never mind. It is recording.
It is recording. Yeah, it's all good. Yeah, I messed up. We tried to do it. We had a call a couple weeks ago with Noah about some of this work, and we could not get Zoom to record it. So another strike against Zoom. I've been, as much as WebEx is sometimes a pain, I've actually had the most reliable experience with that so far. So we are recording. So without further ado, this presentation is called Precipitation and Flow Frequency Analysis using Stochastic Storm Transposition. And mostly what I'm going to do is I'm going to kind of highlight the journey where we go from traditional design storm modeling onto sort of what our nexus is, what the next steps and the things that we want to do are going to be. So let's see if this will advance. So the first thing I want to do is I want to talk a little bit about future flood risk data. I'm not going to get into too much detail on this, but I do want to identify the things that FEMA is doing that require us to do something different. Because anybody who's done any floodplain type mapping or modeling before, you're kind of used to how some of the cookbook might work on that. And we're really flipping the script with some of the ways that we're approaching this problem now. And a lot of those come from what FEMA is requiring as part of their goals with the Future Flood Risk Data Initiative. I'm going to highlight Stochastic Storm Transposition, which is our proposed solution to these problems. I'm going to talk a little bit about what we've done so far to get SST and some of the other modeling things that happen in conjunction with that into some of our tools, and then just a short little discussion of some of our opportunities as they come on in the future. This little flow chart is kind of a stock graphic that was generated for FFRD, but what it does is it highlights a few of the key areas that represent a pretty big change from the way that we do things now. The first being this notion of the shift from binary to probabilistic analysis. So anybody who's worked with the firm before, a flood insurance rate map, you usually are used to finding your 100-year floodplain, your 500-year floodplain on the map, and the binary designation usually has to do with the mandatory purchase of flood insurance. If you're inside the 100-year floodplain, you're buying flood insurance. It's that mandatory purchase. And that binary distinction has led to a lot of problems in terms of the hazards that it actually increases. It makes people make poor decisions. And then the map is used for a lot of things that it shouldn't be used for. And so FEMA is really seeking, among other reasons, to improve this mapping process by fully graduating this and getting a full picture of the flood hazard from the source of flooding all the way out into any part of the watershed. And that includes areas that are completely off of a river. There's other elements of this that touch a little bit of what we're doing with the storm modeling, but really the shift from binary to probabilistic analysis is the main place that what we're doing is motivated by. The data management delivery part of it is also important because the framework that we have, or at least we're proposing, lets us update regularly. So if we have new storm data, if we have new information, we can incorporate it very, very quickly. For a lot of flood insurance mapping products, they're dependent on things like NOAA Atlas 14, which either are pretty stale at this point or may not even exist for the area you're doing modeling in. And so we want to avoid pitfalls like that as we roll out estimates for flood hazard anywhere in the country. So let's talk a little bit about traditional frequency storm modeling and kind of what FFRD has to say about that. But to meet FEMA's needs, we got to do a bit of work here. There's a few things that we just can't take off the shelf and implement and call it good right now. FFRD requires us to be able to estimate flood hazard at any point within a watershed. Traditionally, we look mostly at hazards that are close to a river. We're not really looking too much, and this kind of leads into the second point, of fluvial and palluvial hazards. So that's both flooding that comes from a river and flooding that can happen off river, usually due to things like infiltration excess, run-on, stormwater conveyance issues, things like that. But we have to be able to look completely any point within a watershed, not just a handful of key damage areas, at what the flood hazard might be. And you can already imagine, if you've done traditional design storm modeling, how that can be really challenging to do. FFRD does have consideration for coastal hazards in here. And I would say that coastal hazards are really a place where we've had a blind spot with design storm modeling in the past. We've really not worked in concert with the coastal community very well. And I think this is a great opportunity not only for what FEMA is doing, because coastal is a huge part of what FEMA does. It's also an opportunity for us to be doing things better. And so we're working to make inroads with the coastal community, not only within the Corps, but in other agencies, to do a better job of doing considerations in our design storm modeling approaches for coastal hazards. We have to be able to compute hazards across the full spectrum. So we can't just be looking at a couple of key frequencies like 100-year or 500-year anymore. We have to be considering everything from the routine to the rare. And being able to do that requires us to have a much finer granularity on the inputs than we would have with just looking at the standard frequencies that you would get out of something like Atlas 14. So the process we propose has to be able to look at that whole range. And then the last part, this is obviously important for anything that we're doing. Atlas 14 doesn't address this. Atlas 15 Volume 2 will address this, or at least intends to. But how do we deal with non-stationarity? And that happens in more ways than just climate change. That also has to consider things like land use change. But how do we take this process that we use for mapping flood hazard and take into account the fact that things are changing underneath our feet? So the reason that the hydrometeorology part is so important in all this is, for the most part, meteorology is used as the basis for estimating the frequency of the hazard. So in the process, and I'll show a little flow chart in a second, most of the time what we're doing is we're running some design storm event, which has a known frequency that we get from a frequency analysis. And we take that, we translate that all the way through the process, and we assume that the flow that we get is equal to the probability of the precipitation we started with. And so when you go back to that very beginning, getting the frequency of that precipitation right is really, really important, because it's in the driver's seat for estimating the flood hazard. It's the thing that we're going to use the most for getting to our flow frequency. Now, we do combine that with other things. If you actually do a stochastic analysis on those precip events, sometimes you do get uncertainty around them. Sometimes in really sophisticated analyses, we use the full continuum of precip and those sorts of things. But most of the time, it's going to be coming from those discrete events. And so what we have to do in order to meet the goals of FFRD is we have to be able to go from binary to graduated. So we're not just dealing with a handful of frequencies anymore. We have to be able to do this anywhere in the country. And this is being rolled out everywhere. The intention is to be able to cover the entire country with this methodology. And then we also have to be able to regularly update and reevaluate it. And so all of these things really tell us that we need to be pursuing a data-driven approach that can be quickly scaled and applied anywhere within the United States. So for anybody who's done this or not done this before, this flow chart illustrates how we usually do flow frequency modeling based on precipitation events. So what we do is, if you go to the left side here where the depth, duration, frequency box is, that's where we get our information about the relationship between the duration of rainfall, the amount of rainfall, and its frequency. So Atlas 14, one of the most famous products for doing that. Atlas 2 is one of its predecessors. There's also various TPs and other documents that cover this. But the idea here is that you take a very large number of precipitation gauges and you analyze the annual maximum rainfall from those and come up with a relationship between the depth, the duration, and the frequency of that rainfall. Now, when you get those values, say you've now chosen a frequency, like the 100-year rainfall, and you want to take that and apply that to a hydrology model, there's a bunch of other stuff you need, because that volume of rainfall by itself doesn't mean anything for how the model's going to respond. So we have to add in a number of characteristics that turn that depth into a design storm. And that usually includes things like, how is that rainfall split up in time? How is it split up in space? How do we take the fact that our analysis was done on a rain gauge by rain gauge basis for a very tiny area or a point and apply that over a watershed average? And that's a process called area reduction. And so that combination of things helps us have some input precipitation that we can then put on a hydrology model. Now, our hydrology model has a number of assumptions baked into it as well. We've parameterized it in some way and chosen our processes if you're using something like HMS. You've probably calibrated the model, and so you now have model parameters that make it somewhat reflect reality. And then you also have initial conditions. So prior to this rainfall event, the watershed's in some state that may make it more or less flood prone. If soil's saturated, if there's significant snowpack, there's high channel flow, all of those sorts of things that make it, when you then drop the rainfall on it, that the response is going to also be affected by those initial conditions. But you have to assume those. And so the combination of these things, that design storm you've created and the hydrology model's setup, allows you to do peak flow frequency. You know, I suggested you choose the 100-year first, but you might go from, you do the 2-year, the 5-year, 10-year, and so on, all the way up to the 1,000-year per the frequencies in Atlas 14. And by running those through the model, you can then get a peak flow frequency curve. The trick with all of this is that you get discrete results by frequency and by location. So what you're not getting is a full parameterized probability distribution that allows you to do any sort of inference from it. What you're doing is you're getting one result for each run of the model for a location. So for example, if you have a damage center within your watershed that you're concerned about this for, you'll have a model built that lets you do all of the modeling down to that point, and you'll apply the correct design storm characteristics to take that depth, duration, frequency information and run it to get a frequency flow. So you run that event, you extract the peak flow, you plot it on a frequency curve. This is all based on the assumption that the resulting flows that you get from running this hydrologic model, that they have the same frequency as the input precipitation events. That's a concept called AEP neutrality, or annual exceedance probability neutrality. You're basically setting up the model in such a way that it's reasonable to assume that the flows have the same probability as the input precipitation. So that is very limiting in a lot of ways, because we know that you can get big flows from a combination of relatively moderate inputs. You can have really big rainfall and hydrologic conditions that result in less runoff. Those sorts of things are the nature of hydrology. And so by doing this sort of design storm process, you have to sort of assume some of that stuff away. And that's not always the best way to portray the risk accurately, especially when you're trying to do this modeling for an entire watershed at a time. One of the most sensitive parts of doing this is the assumption for storm area. So I mentioned depth area reduction, and if I had a nickel for every time I reviewed a study, either core or external, especially contractors, where somebody forgot to apply area reduction, and I had a nickel for that, I could retire, because so many people assume that they could take the NOAA Atlas 14 grids, apply that as a storm to their watershed, sometimes at huge areas, 1,000 square miles or more, and that those results are valid, and they're not, because those are coming from point precipitation data. If you want to apply that point precipitation data over any appreciable area, you have to apply area reduction. So area reduction is a generalized form of a storm spatial pattern that relates the point maximum, so the largest amount locally for that precipitation event, to what the area average would be. We know it can't rain cats and dogs over a huge area the same way that it could at a small point. And so if that area that you're accumulating rainfall over gets bigger and bigger, the amount that you go from that point maximum out to an area average reduces more and more. The curves on the left here are from an old publication that still gets a lot of use today, called TP40. Those curves get tons and tons of use, but they are based on a very limited sample size and are highly generalized. These don't look anything like the variability that you get from real storm to real storm. But the trick is, if I had a watershed like this one that I'm showing here on the right, and I wanted to do modeling all the way down the channel, so I've got this little damage area here up towards the top at about 6.6 square miles. If I wanted to do modeling for that, I'm going to have very different assumptions about the area average precipitation above that point than I would if I was modeling all the way here at the outlet at 93 square miles. And so you could see that for small areas here, if I'm at 6 square miles, the ratio of the area average to the point maximum, it's close to 100%. But when I start getting out to, say, 93 square miles, like here at the watershed outlet, I have to reduce that by, more than 10% off the top. The trick here is if I wanted results at every single pixel of this streamline all the way down, I'm accumulating drainage area and therefore storm area as I go all the way down, because we make the assumption that the storm area, the area where it actually rains, and I'm taking the average, is perfectly coincident with the drainage area. So that's a conservative assumption, because what it's assuming is that the largest, say above this point, 6.6 square miles of rainfall is occurring exactly in the 6.6 square miles that perfectly coincides with the squirrely shape of this watershed above it. So it's a conservative assumption. But we have to apply it, because otherwise we'd be over applying our frequency rainfall potentially by significant amounts. Now, pluvial hazard's a particularly thorny problem, mostly because you can't just take flows in the channel and do inundation mapping based on that. What you have to do is you have to have a good understanding of the lay of the land and its interaction with the storm patterns that you get as they fall. Because locally intense precipitation or highly variable precipitation patterns can drop very heavy rainfall in locations that are far off the channel. And due to the hydrology and hydraulics of the situation, you could wind up with significant depths of water that cause flood damages that otherwise, if you were only modeling flows that left your channel, that you would never capture. And so this little map here, you could see how it's got a little bit of that shading in there that indicates the depth of water. You get the common places where water likes to accumulate during heavy flood events, for example, highway underpasses, and other low spots. It's probably a detention basin there. But there are areas in here where you get flood damages due to localized ponding that if you were just looking at a channel overflowing, you would never capture. And the only way we can do that is by appropriately capturing the spatial variability and intensity of rainfall over a watershed and its interaction with the landscape and how it captures that water. I did mention coastal and what we would call compound flooding events. We really need to do a lot of work to reduce the seam between inland and coastal flood hazard estimation, mostly because using precip frequency information in conjunction with, say, tropical source or coastal hazards is really limited and really challenging. The storm events that you see for coastal stuff, obviously they're coupled with high winds, heavy precipitation that comes in intense bands that spin off of a storm that would appear like this. And so right now, the methods that we're using to try to do that kind of modeling in the inland hazard area is just not going to capture that sort of thing. And so what we have to do is do better than that. And we can actually use tools like stochastic storm transposition, which we'll talk about in a sec, to capture that and to actually couple up those processes so we can capture these sort of compound hazards where you have significant channel flow coming down, potentially a storm making landfall coming up, and the floods that can result from that combination. Now, systems modeling is an important part of this too, right? Because with the systems in place, we usually try to manage flood hazard in a way that reduces damage in maximal way, an optimal way. But floods don't always cooperate in a way where they fall over all the controlled areas or protected areas within the watershed. And a lot of that happens due to the nature of storms and the way that their precipitation varies in space and time. When we manage these things, we do transfer risk in place and time. If you have two subsequent flood events, you may have made a decision during the first one to reduce damages for that event by operating dams, for example, to reduce those damages. And then you get a second flood event that then sort of violates those assumptions, right? You've stored water in some places that now have nowhere to go with the additional water from these storm events. And so we have to capture the fact that sequential events and systems can change the way that flood hazard looks throughout a watershed. All right, so let's get to the exciting part. Let's talk about stochastic storm transposition. So what SST is it's a fancy way of moving storms around. That's not going to end my talk there, but what SST really does is we take a large area that we think that storms, if they occurred in one location, could have occurred at any other location within that domain. That's the transposition domain. What we want to do is we want to find a box, and they're not usually boxes, they're usually not so friendly like that. But we want to find a domain that captures that meteorological homogeneity around our target watershed. So say we're working with this little gray watershed polygon right here. What we would do is we would find a region around it in which if a storm occurred there historically, we think that meteorologically speaking, it could have occurred at any other location within that watershed, or not that watershed, but that domain. Because what that's going to let us do is resample those storms that we've seen and move them around in space, because we've now established that we think they could have happened anywhere else. So you could see what might have to go into creating one of those transposition domains. You have to make consideration for what kinds of storms can occur. Are they tropical? Are they extratropical cyclones? Are they mesoscale events that include heavy convection? Are they localized ordinary thunderstorms? You have to look at the relative frequency of those events and consider a domain that roughly has the same relative frequency of those events. You have to consider things like, how close am I to a coastline? How close am I to a mountain range? Do I have to worry about rain shadow effects? Do I have to worry about orographic intensification of these events? Do I have to worry about, moving convective type of events to locations that don't experience deep convection or can't support it? And so this domain involves a lot of meteorological judgment. And so one of the things that we're working on is engagement not only with the Army Corps of Engineers meteorologists, but also meteorologists from other federal agencies who can help us build up the expertise to consistently draw these domains for watersheds that we study. So what we do in that domain, though, is we go back into the historical record and we build up a catalog of historical storm events that have occurred within that domain. And the idea is to take multi-sensor or other gridded precipitation products and basically have an entry for each storm event that occurred. And that entry contains time-space fields, usually raster data, time series of that, so that we could take a storm as we would have seen it. So imagine it, if you've ever looked at NEXRAD radar or any of the other stuff that they show real-time precipitation with, that evolution of a storm event, we want to preserve that in space and time. We want to keep that full picture. We're not reducing it to a point maximum or an area average. We're not reducing it to a DAD table. We are taking the time series of rasters and preserving it in the catalog. Then what we're going to do is we're going to not just keep an annual maximum, because an annual maximum is kind of a tricky thing when it comes to those storms. What we're doing is we're keeping the largest several storm events of each year in the historical record, and we're preserving them wholesale. So now if you have a year that had a number of significant events within that transposition domain, you're going to keep all of those. Because when we go through the process to actually do the simulation to understand the variability of rainfall, we're going to sample multiple of those storm events per year, just as it occurred that there were multiple of those storm events per year. What this does over this big region is it gives us space for time substitution. So what we get to say is, because this area is homogeneous, and because I'm choosing a number of independent storm events that occurred throughout this domain, I am building up a catalog that represents more years of record than there are in the period of record. So for example, if I'm using a data set with 40 years of observed record, each of those years has a large number of independent storm events. So now my sample size is much greater than just assuming any sort of annual maximum process in this whole thing. But the great part about all of this is at no point have I done any analysis to fit a probability distribution to this data. I've not reduced any of these observed storm events down in any sort of way to generalize them. What I'm doing is I am trying to preserve the real space-time properties of these storm events so that I can then turn it around and say, okay, if I move these storm events around in this homogeneous domain, what does the variability of precipitation look like in my target watershed? And that's how this whole process works. Now, this has a long history. This isn't really a new idea. Back in 1962, Alexander proposed that we could do this sort of thing, but it wasn't until 1989 until we had a paper that kind of sketched out the math that proved that it made sense. The early attempts at doing this, they didn't have a lot of great multi-sensor products or radar-based products or anything that could really make it easy to take real storm events and do this. And so a lot of the data that was used in these early studies was based on the Army Corps of Engineers storm catalog. And if you've worked with that, you know what it contains and what it doesn't contain. And what it doesn't contain is detailed space-time patterns of storm events. A lot of these are reduced down to DAD tables, depth area duration tables. So what we've had this revolution of in the past decade or so is data that's been available for us to take these observed storm events and not have to reduce them down in any sort of way. Is just take the observed storm patterns and keep them and use them in their detail. So better detailed data are very helpful. Longer periods of record for these gridded precipitation data sets is valuable. All of these things have allowed us more recently to be able to take this process or this tool, SST, and actually apply it in a meaningful way. Because with the storm catalog, you're looking at the worst of the worst. Most of the storms in the storm catalog, the core storm catalog, are aimed at things like probable maximum precipitation. They're used at establishing what credible upper bounds are for how heavy it can rain over large areas. We're not thinking about that. What we're thinking about is that, like I had mentioned in the FFRD goals, that nexus of what's the 2-year to 2,000 year look like? Not what does the 1 in 10 million look like? So it's really been data that's been allowing us to make this advance and actually get to a point where we can do this operationally, because there's also the, oh, Carl, that's a great question, the storm catalog. I'll mention that in a second. But we get to a point where we can actually move these around because we have computational power to do this as well. A lot of the early studies couldn't do a full Monte Carlo simulation of these storm events simply because taking the data, moving it, and then intersecting it with a model was so computationally expensive that you couldn't run huge numbers of simulations doing that. That's something that we can do now. So Carl, to your question about the core storm catalog, there was an old document back when it was the War Department that it was originally put together to chronicle storms of note, usually ones that were at the very, very tippy top of the upper end of extremity in terms of storms. They catalog these, and a lot of them, they have varying amounts of data that support them. Usually at minimum, what they have is like some storm accumulation contour map. Some of these are very old. These go back sometimes to the late 19th century. And what they're meant usually for is doing probable maximum precipitation analysis and saying, okay, we have the storm event that was probably one of the largest of its kind. What are some of the properties of it that make us think that it was approaching the hardest it could possibly rain over a point over a large area, or how much could that storm have been intensified to represent a maximum? And so it was originally these paper documents that were used to this end, and now there's actually, you can get these things online. They're not fully digitized, but a lot of that data is available through a portal, I believe, that the RMC maintains. So if you're ever curious about that, get in contact with John England at the RMC. Here's an example, actually, of a set of storm contours in the storm catalog. And you can see here that when we have real storm events, that they vary significantly in space and time, that using really nice generalized patterns isn't really going to get us to the real variability that happens in these storm events. You can see this one's got multiple centers. We've got several places where there's a 12-inch contour here. You can see one here towards the south, a couple up here more towards the center, and one up further towards the north. These sorts of real things are very challenging to model when you use precipitation frequency products because they assume that there's a single point maximum. In this application, we call that the single center assumption. Real storms don't behave like that at all. And when you look at the impacts of a storm event like this, it's very clear that getting that spatial pattern right is critical. And so when we use SST, we preserve this. Now, ideally, what we would have is hourly radar time slices of the precipitation that occurred for this, so that we could take it from where it occurred, move it to another place, and see what the impact was. With the storm catalog, most of the time, this is the amount of data that we get about a storm event, right? So we got like the 20-inch maximum right here. We got all these other localized centers, but we don't know when they happened relative to this storm event. It could have been in the first hour, could have been in the last hour of 72 of them. We don't know. Usually a lot of times you might have gauges here and there that help substantiate it, but the real evolution of that storm pattern is mostly unknown. We use the SST process, and what we're doing is we'll sample a number of storm events per year, we'll transpose them somewhere else in the domain, and we go and we compute either our precipitation or flow frequency. We don't have to make any assumptions about the frequency of our results. We don't have anything that tells us before we start what the frequency of the event that we're running is. We won't know until the end, and we get done with all the transpositions to know what's going on. Now, the real big upside to this is that we can analyze flow frequency or depth frequency everywhere in the watershed. That's because we don't have to make any assumptions about area reduction, which are dependent on drainage area and storm area. And then when we transpose these, and I believe I have a flow chart. Yeah, I'll show the flow chart, which will clear this process up in a second. But when we do these transpositions, you move it, you run it through your hydrologic model, you can go to a number of damage areas or areas of location within your watershed, and you can pull a flow frequency curve from the annual maximum transpositions. The beauty of this is you don't have to know before you start whether it's going to be an annual maximum for one location or another. You don't have to assume any transposition is the annual maximum for the whole watershed. And that's really crucial because sometimes you get storm events that are highly localized to one area that might cause an annual maximum event in that sub-drainage, but doesn't for the rest of the watershed. And so it's crucial to be able to capture the fact that different storm events within a watershed are going to cause the annual maximum. So here's the procedure. More flow charts, because I like flow charts. The way this whole thing works is you start by selecting a storm from your catalog with equal probability. So a catalog contains multiple storm events per year, usually from a long period of record. So let's set this number. We'll say there's 400 storms in our catalog. That's a pretty good number. What we do is we select one of those storms from the catalog with equal probability. We're making no assumption about the frequency of any of those events. Then what you do is you take it and you move it from where it occurred in reality to a new location within your transposition domain. And the transposition is also done with equal probability. That means that the transposition has a uniform distribution in both its x and its y coordinate. Now, the transposition domain isn't always a rectangle, and so sometimes they have kind of odd shapes that really try to capture the meteorology in that area. But when you move it around, you're basically assuming, going back to the definition of our transposition domain, that that storm is likely to have happened at any other place within that transposition domain. And so we're going to take advantage of that assumption. We're going to move that storm to a new location. What we can do at that point is we can do one of two things. We can either compute the watershed average precipitation, which will give us a frequency curve for the watershed average precipitation, which is actually very useful, or we can run a hydrologic model, just as we would in the regular design storm approach, and then we could start to look at the resulting flows. Now, this is all based on basically brute force Monte Carlo, which, if you know me, is one of my favorite things in the whole world. If brute force isn't working, you're not using enough. The way this whole thing works is you have a multi-year simulation. So we'll talk about this in terms of synthetic years of simulation. When you do anything with annual maxima, if you want to get out to a frequency, you usually have to simulate based on plotting position estimators usually out to that frequency. It's in years. So for example, if you went after the 1 in 1,000 event, you have to be simulating at least 1,000 synthetic years, absent any kind of other sampling scheme that lets you get out to those frequencies. So if you're getting out to the 1 in 1,000 event, you're running at least 1,000 synthetic years. Per synthetic year, you are generating anywhere from 1 to n storms, where n has a probability distribution, some counting distribution, usually a Poisson distribution, and the average rate of those storms comes from your catalog. So I said we had 400 storms. Say it was 40 years of record. That means the average rate of storms is 10 per year. Each synthetic year, you're going to generate some count of storms from 1 to n. Say this year is 7 storms. I'll pull 7 storms from the catalog. I'll transpose them somewhere else within the watershed. I'll run the model 7 times. And then at every point in the watershed that I'm interested in annual maxima, I pull the annual maximum result. And that's how that whole thing works. Now, what storms are, and I've alluded to this because I've mentioned multi-sensor products and radar data, but the idea is that they're fine resolution representation of severe historical events. That we want to get down to fine scale precipitation data as much as we can, because we want to resolve all of the key features of these storm events that creates flooding. The storm events that we get, they're all from that big meteorologically homogeneous area around the watershed, because again, we're assuming that that area has been drawn with enough care that the storm events, wherever they occurred, could have occurred somewhere else. The worst storms are measured by basically their average accumulation over an area the size and shape of our target watershed. So the map on the right, this is from the Storm Sniffer 2000, which is a tool written by one of the FEMA professional technical services contractors. What this shows is a few things. The whole rasterized space here, I wish I had a background map, but I don't. The whole rasterized space is the transposition domain. This is the Kanawha watershed in West Virginia. So we've done a little bit of work there in the past. There's Bluestone Dam that lives in that watershed, and there's a number of other core dams as well. This gray outline is its real position. This raster represents the total storm accumulation for one event from the catalog. What the solid black line is what happens if I move the watershed polygon within the transposition domain to a point and I optimize its location to capture the most rainfall possible. And that's exactly what this procedure has done. And that's how we sniff the storms out of the catalog. That's how we identify them. As we take the watershed boundary, we move it to another place within the domain so that we make sure we don't get outside of the domain. And then we basically compute the area average rainfall and say, is that storm severe enough for us to keep? And if it is, then we keep all of the rasters that are associated with that storm event. Usually we're talking about 72-hour storm events. We're doing a little bit of work to figure out if there's sensitivity to the duration of these things, but usually they're 72 hours. And so we have, in this case, we're using a data set called AORC, which works really well for hydrologic modeling. The resolution is 4 kilometer on this particular set. There's also a 1 kilometer data set available that we're working on using. And they're at 1 hour. And so you're dealing with 72 1-hour rasters at 4 kilometer resolution. Just for a sense of scale, the Kanawha watershed is about 12,000 square miles. So if you were doing this with precipitation frequency, you'd run into some serious barriers to application at a scale this big. The highest recommended scale I would ever suggest anybody use point precipitation frequency for a watershed is usually somewhere around 6 to maybe 9,000 square miles. So using precipitation frequency rasters for a watershed the size of the Kanawha is just not possible. And so SST is our way about doing that. And what we do is when we sniff these storms out, we keep multiple events per year. Either we keep, say, the top 10 per year or top 15 per year, or what we do is we find what threshold we believe is kind of the smallest end of our large credible storms, and we just keep all of the storms with an average accumulation above that threshold. Now, I do want to visit these fundamental assumptions again, because these are the things, these contrast what we do in a traditional design storm modeling approach. First, we have the notion of this transposition domain, that we have to be able to assume that we can freely transpose a storm from any one location to any other location in the domain. We also have to assume that the data that we have, so for example, measured by the AORC or other precip data sets, adequately capture the real rainfall that occurred, because that's going to be the part that really drives how our frequency analysis turns out. We also have to assume that the catalog that we build out of all of these storm events that have occurred, that it's representative of a sample of the severe meteorology in that area with the right relative frequencies. It has to sufficiently describe the hazard. So the cartoon on the right, this has actually got a base map. So if you wanted to know where the Kanawha Basin is, that's here in red. What this red kind of jagged boundary is, that's the transposition domain, and it's been reduced so that no storm could ever fall, so no significant rainfall for the storm could fall outside of the transposition boundary. So there's this whole issue of the fact that our watershed's kind of a strange shape. And so we want to make sure when we move storms around within that domain, we've restricted it to places where we're not getting basically rainfall that would have come from outside of the transposition domain. And so the procedure here, you can see this is 10,000 points that filled the space. They were drawn at random using QGIS. This illustrates what you have to do in a irregularly shaped transposition domain where we can't just assume like, you know, a nice neat square. And I'm going to show a demo of the square in just a little bit, just because that makes life easy. But the reality of this method is that we have to space fill irregular polygons often, which is a little bit more work. Now, how do we get to flood frequency? So I mentioned for the design storm stuff that we had to make some assumptions about hydrologic model parameters and initial conditions. And what we use with SST is what I call a quasi-continuous hydrologic modeling approach. So instead of running a full, very long, continuous simulation, what we do is we spin up the parameters of a model that's been calibrated with an event date in mind, not unlike what happens in HEC Watts Hydrologic Sampler, where you do event date sampling. And the goal here is you tell me when an event occurred, you go and you get parameters from a period of record continuous simulation that are reasonable for the date that you pick. So say I pick March 14th. I go back to the historical record and I go look at, hey, give me all of the model states from this continuous period of record that I already ran that would be reasonable for March 14th and draw one of them at random. Set the model in that initial state. Maybe you do some parameter uncertainty on your calibration parameters. You randomly sample those. You randomly transpose a randomly selected storm, and then you run it. The key here is it captures the variability in some key state parameters that can change the amount of water that's in the system and the runoff response, things like soil moisture, snowpack, channel flow, those sorts of things. What I wanted to show here is this framework was used by the Bureau of Reclamation in a pilot study they had done. They had done this in the Front Range in Colorado, which has a very nasty mixture of snowmelt, rain on snows, and pure rain floods in that area. And so they have these shoulder seasons where the two major flood causing mechanisms tend to make it really hard to get model states right. And so they set this up to use their quasi-continuous framework with SST to be able to capture that mixture of these things and set up the initial conditions plausibly. So you sample those event dates from a seasonality distribution, so you know when the storm events tend to happen. So if you know, for example, we're sampling mostly heavy rainfall events doing SST, we're going to more heavily, capture that based on that occurrence density that we see on the plot. I mentioned that the historical barrier to this was data. Really, it hasn't been until I would say the last definitely 5, maybe as long as 10 if you're being generous years, has really been a renaissance in data for like long record, high resolution gridded precipitation products. It's come a long way, and that's been a blessing for a number of modeling applications. We've done a lot better job calibrating hydrologic models with better boundary condition data. It makes better models. But this also lets us do a more thorough analysis of these storm events. We couldn't do SST without good radar data. It's that simple. And combining that radar data with other things like gauge data, like satellite observation, like data assimilation products through things like numerical weather forecast models, these things really help us do this kind of modeling. And so here there's a number of data sets that are radar multi-sensor reanalysis. The ones in red have been used in a historical SST study. The other ones have not yet, but they are worth considering for some of these applications. But the key to all of this is optimizing the quality of the data, the period of record, and then our resolution of this data. And so the current front runner for our application is AORC. If you're not familiar with it, I highly suggest going and looking it up. AORC stands for Analysis of Record for Calibration. It's a weather service product that's distributed on an RFC by RFC basis. It's a really good data set. It works great for hydrologic modeling, and it's been working great for our SST process. There is a 1 kilometer product available, and we're working on using that as well, because that additional resolution will be really valuable in smaller watersheds. But with the new data, that makes it possible to do this stuff. So let's talk about how we're getting this into tools so people can use it. The first thing I mentioned, the Storm Sniffer 2000, that's the kind of halfway joke, but sort of serious name that was given to the tool developed by Dewberry, who's a FEMA PTS contractor. It's got a web interface, so later you can go click on this link and you can see what we're doing with some of our studies that are going on right now. But the goal is to be able to identify the most severe storms for our target watersheds. So it takes an input of our target watershed and our transposition domain for that target watershed, and it helps us identify which are the most severe storms. To build a catalog, I mean, you could just look at how severe the storms are, but you have to have criteria to choose which ones you think are severe enough to keep. And so there's advanced filtering capabilities in here that let us kind of parse all of the data that we've got into a neat little catalog of the selected storm events. This also performs data extraction and conversion. So a lot of this source data coming from AORC is all in NetCDF format. We're outputting it all in DSS because it's being used in HEC-HMS. This also automates HMS input files, which is really, really fun because I can generate an HMS grid file that contains only the selected storms. And so what I literally have to do is take the DSS files it gave me, the new grid file, put the DSS files in my HMS data directory, put the grid file in my project directory, and I can open HMS and all the grids, hundreds of them, are already in my model, which is really, really slick because I can just get these things up and running really, really fast. The other parts of this, and I'll show this in some of the HMS implementation stuff, is the part where we pull out the names so we can randomly sample the storms and things like that. So within HMS, HMS leverages Tom Brower's Vortex tools to do transposition of these storm events, and it runs really, really fast, which is cool. So what we do is we take these and we run them in the uncertainty analysis framework in HMS. And if you haven't played with that yet, I highly recommend playing around with it because it's a lot of fun. Down in the lower left here is just a little thing that shows some of how the uncertainty analysis works, but you could specify hydrologic parameters, and now you can specify meteorologic parameters. How do you want to vary them is essentially the way this whole thing works. Is you set up a sampling scheme for these parameters, you run the simulation, you run it a large number of times, and you look at the variation in your output. And the uncertainty analysis gives us a natural framework that was already within HMS where we just had to say, okay, now I want to randomly sample the position of my storms. And it can do that very, very quickly, which is super cool. It was amazing how fast we were able to stand that up. It took a little bit of work to identify, for example, where's the center of the storm where we observed it? How do we tell it, where is it being moved to, and so on. And you can see in here that all it takes for the user then is to specify a uniform distribution for the parameters. Now, in its current state, HMS doesn't have anything that lets you sort of bound the sampling to an irregular polygon. So what you can actually do, instead of using a simple distribution like this, using the uniform distribution, you can specify the points. So you can pre-generate them, like I showed in QGIS, and then you can import those to HMS already to go, and it'll randomly sample from those lists. We can also try to tackle some of the complex hydraulic routing by using the 2D overland flow feature, so our 2D transform based on the RAS diffusion wave solver, which is really, really cool. You can do the meteorological part and the full top to bottom hydrology and hydraulic simulation all in one stop, which is really cool. So anybody who hasn't seen some of the 2D outputs in HMS, this is just a quick little illustration of some of the stuff that you get, for example, max hydraulic depth, or your cell velocities, things like that. But this is all run with a transposed storm event, which is really neat. So I'm going to show a little mini pilot. We're going to hit some road with the rubber here. I've got a little HEC 10. This is a pet watershed of mine. I've done a ton of studies in this area. It's 93 square miles in east central Iowa. It's a mixed agricultural and urban watershed, so there's a significant damage area down here. So this is Marion, Iowa, and then this is Cedar Rapids right here, where they're building a big levee right now. But so this has a pretty significant damage center. There's a USGS gauge down here. It only operated for a little bit of time, so we don't have a ton of calibration data here, but we want to prove that we can start to hit some of the targets by using SST. So what I did is I built up a catalog from the AORC 4-kilometer data set from the North Central RFC. It has a period of record of 1979 to 2022. It's about 44 years of record. And what I did is I retained any storm event that averaged 72 hours of precipitation, or over the 72 hours over the watershed area, over 3.941 inches. And you'll ask, well, why did you pick such a strange number? That's because that gave me exactly 10 events per year. So each year has a varying number, but it gave me a nice round average rate. So I picked a threshold to do that. And then the transposition domain for this little purple watershed right here was roughly the state of Iowa. So anybody who's familiar with the meteorology in the Midwest knows that there's not exactly mountains or other interesting things going on there. And so there's another study that did transposition for a watershed roughly in this part of the state, if you can see my mouse. And they found that it was reasonable without too much work to assume that the state of Iowa was a reasonably homogeneous transposition domain. And so this is just one realization of running SST over this watershed from that catalog. And on the left side is the results of looking at the precipitation frequency that results at looking at the area average precipitation for the transpositions. So what I've done is I transpose 10 events per year on average. I run 1,000 years of these transpositions. And for each year of transposition, I take the annual maximum watershed average precipitation. And I've plotted that as a black dot. Now, what I also did is I took the NOAA Atlas 14 precipitation, the point product, and I've averaged that over the watershed without applying any sort of area reduction, and it's also for 72 hours. And so what you're going to notice is that the black dots fall below the blue line. And I say, that's awesome. That means we did it right. Because the blue line represents that area reduction applied point results, and we have an area average in the black dots. So the difference between the blue line and the black dots is your area reduction factor. And so you could see in this case, if you do not apply an area reduction factor going from the point maximum to the area average, you would overestimate the precipitation. And in some of these cases, we're talking about 10% or more. And so that's a significant difference. So the results on the left side is exactly what we expected to see. The area averages are lower, but that the shape of the curve follows that roughly the same. Now on the right side, this is running with the hydrologic model put into place. Now this is not running 2D. This isn't running anything that captures nonlinearity, and that becomes evident in the results. There was one event that I calibrated this to, and I know that it's a cardinal. The USGS gauge was operating for a grand total of about 5 years, and there was one. I think that's perfect timing. I said I calibrated to one event, and Mike Bartles left the meeting. That we calibrated this one event, which, if you look at it after the fact, was about a 25-year event. The trick with this being, we just had nothing else. There were no other major floods in there, and the response of the model looks really, really good up to the calibration event magnitude. So this is compared against stream stats. I don't have any bulletin 17 analysis to do here because, again, the gauge was only operating for a couple of years. And stream stats isn't necessarily the gospel truth. It has its uses and its abuses, but in this case, we tracked pretty well up to the calibration event magnitude. And this is using a conventional Clark unit hydrograph, which suggests to me that doing things like either 2D simulation, which is computationally expensive, or something like using the variable unit hydrograph method within the Clark to capture some of that non-linearity that we get in that response would be pretty valuable, mostly to be able to extrapolate beyond that calibration event magnitude. But the results are promising, especially considering the model quality we consider particularly high. We had a 2D model that Josh Willis built for this, and I had hoped to do a lot more with it prior to putting together this presentation originally. I did end up building out some mod Clark curves for it. I haven't been able to do a simulation with that yet, and I haven't done a fully coupled simulation yet. But the mod Clark response looks, or the variable Clark response looks about how you'd expect it to. And so it's a really promising way to shortcut running the full 2D, which is pretty cool. So this is the last slide. I've talked a lot, I've talked fast, and I apologize. So I hope that if you haven't completely tuned me out, that if you have any questions, you'll either ask them or throw them in the chat or something. But these are the kind of the key places that we have to be engaging in order to keep moving forward on all of this. The first is, how do we develop transposition domains for any watershed in the US? And it's got to be consistent, and it's got to be something that makes a lot of sense, meteorologically speaking. And so we're hoping to engage with NOAA on this, actually. It seems like an area they seemed really interested in, because it's also got impacts for probable maximum precipitation, because that uses transposition techniques as well. So we're working to collaborate with the meteorological community within the Corps, and also with NOAA on helping develop those. We also have questions about data, right? So I've really become attached to this AORC data set. But what other data are fit for this application? The question of, is this data set representative of the storms as they actually occurred? That's a really good question. And so I am totally open to seeing new data sets and trying things out, as long as they help us meet the goals of having a long period of record, good fidelity, those sorts of things that we can use for doing this kind of modeling. And so going down that road is going to be really important. We've talked about storm typing. So what storm typing is the art and science of explaining the meteorology behind the precipitation. And it has significant impacts on how we apply the precipitation to the watershed, because certain storm events, right, they occur during certain parts of the year. For example, tropical storms have a season. You would not want to apply tropical storm rainfall on initial conditions that are from March. That doesn't make sense. And so the classification part helps us build out a better catalog. It also helps us in our hydrologic modeling application. The trick is, it's not always very straightforward to identify the exact meteorological cause of a storm event. Tropical storms are probably your easiest one, but when you start getting into really complex synoptic scale events, some of these mid-latitude cyclones or extratropical cyclones have strongly embedded convection. Are those significantly different than something like a derecho or a mesoscale convective complex or something like that? They have a lot of things in common, but they're also pretty different. So those sorts of things are really important to make that distinction. Now, one place that's really cool is we just had a new START work unit, an R&D work unit under the Flood and Coastal Systems program on improved hydrologic modeling of probabilistic storms. What we're hoping to do is use SST as a tool for answering some of the questions that we have, so that people can do a better job of still doing the traditional modeling stuff better. Some of that guidance is ancient. Like it's in terms of like how so many of the other parts of the science have come along, it's been left in the dust. And so we want to be able to still reach back and support those typical modeling needs. And I think that SST could really help us. And we're really offering it up to NOAA that potentially that this could help with the application parts of NOAA Atlas 14 and 15, the places where they've had some significant blind spots in the past. So with that, I thought I saw at least one question roll in the chat. Let's see here. Are all flood events precipitation derived in place? Will, can you give me a little clarification on the question?
Rain falls from the cloud down to the ground. Mm-hmm. Is that the only place that it causes damage? And how does this deal with that?
Yeah, so, well, if you think about rain where it falls and the flooding it causes, that gets to your pluvial hazard, right? So that's sometimes rain ponds in a spot and you get flood damages due to that, or rain falls in one spot, rolls over the landscape down to a low spot and causes damages. Rain can also eventually channelize and find its way to the river, and then the river swells at some other point in the watershed and floods. And so that full interaction of the storm's patterns and the landscape, all of the hydraulic and hydrologic processes that cause a flood, all interact. So wherever it rains, you could have rain that partially covers a watershed. Say it rains cats and dogs in the headwaters, but that causes a huge flood swell that travels downstream where they got no rainfall at all. You could still get flood damages down there. So you don't have to make the assumption of a complete application of rainfall over a watershed.
So I'm pushing because that's what I like to. Sorry, my headset's down. So I have a meeting in 4 minutes, so I don't want to take up all of the headspace here. But what if can rain falling in the Kanawha Basin cause flooding at other locations downstream, not in the Kanawha Basin? And how do you track that?
So yeah, you're asking about the larger scale circulation question, or correlation of losses almost, but you're talking about rain in one place doesn't fall in another. So yeah, the trick is if you assume the Kanawha drains to the Ohio, you don't assume that, that's just what it does. If you assume that you were going to do modeling on the Ohio River and you were going to do SST for a location on the Ohio, what you would do is you would pick a watershed boundary that corresponds to that drainage point or downstream of it, and you would run a catalog based on a transposition domain for that location on the Ohio, which would contain the Kanawha as a subbasin. And you could get results going that way because you could get localized flooding, because we're hitting a meteorological limit here. The storms don't get much bigger than what we're seeing, for the Kanawha, because 12,000 square miles is starting to push up against the upper bound of like synoptic meteorology. So in Ohio River, you're going to get a lot of partial storms, some that can hit the Kanawha and cause flooding in the Ohio. Now the trick is that's a huge domain at that point.
Yeah, I'm not trying to say that we need to go to larger domains. I'm just trying to say that the selection of an event within the criteria of say the storm sniffer is precipitation driven. There could be some exogenous variable that's causing loss in a domain.
Yep.
I'm just so I'm being pedantic. I'm characterizing it within this as a leading question. Yeah, I was doing the same thing in a different point, but snowmelt is another one. I think that temperature driven events could occur as well. And I guess just talking with you about that.
Yeah. So let's look at this really quick. You can't do any of that with precipitation frequency right now. So for the large scale one, there's a lot we could talk about how to do these at multiple scales, and we have, and that's important to think about. The snowmelt problem also has to deal with how do we transpose potentially temperature fields in conjunction with precipitation fields, which is something that we're going to hopefully get going with Dan Wright at University of Wisconsin. A particular research question. And so, even if it doesn't bring rain, then what about, heat waves that cause like our Mississippi River floods right now, right? All that giant snow is letting go and causing havoc on the upper Miss. That's a little bit of precip input, but mostly temperature input. And so transposing temperature is an open question. And then Avital, your question about comparisons with enough bulletin 17C to actually do something. That's something that we're going to be doing in all of the basins that we're running for these pilots for FFRD. That's something that we're going to have to do. And the mixed population part, it's going to be a case of to do the 17C analysis, it's highly unlikely that we will do flood, any sort of separation first, unless somebody really wants some brownie points and wants to go ahead and do that. But, we're explicitly considering the mixed populations when we do it because we're capturing the largest storm events regardless of cause. And we're doing multiple per year. So, if the largest one every year is a tropical storm, but the next 9 are all extratropical cyclones, cool, we're capturing that. So, yes, we do intend to go against 17C, at least compare and contrast, but the 17C analysis is unlikely to contain a mixed population analysis. So, all right. I need to let everybody go. If you have any questions, comments, anything that you would love to talk to me about, I would love to talk to you about it. Send me an email, send me a rocket chat, send me a carrier pigeon. I would love to hear from you on it. Thank you all very much for your time. I thought I'd land this quicker, but I didn't. I apologize. I just get super excited. But yeah, thanks especially to Richard for letting me sign up and give one of these talks. This has been a great opportunity. But yeah, I will let y'all go now. So thank you and have a good rest of your Monday.